Hello everyone. So in this lecture, I'll be going to discuss with you first the gravitational field of the Earth, the equipotential surfaces, that means the geoid and the ellipsoid, the how to measure the gravity, absolute and relatives, and the gravity anomaly. What is elaborately I will describe you about the gravity anomalies and how do we measure the gravity data in real practical applications. What are the corrections? So whole of the gravity lectures will be covered in this slide, and a touch of physics and geophysics will both be there. So let's proceed to the what we know about the gravity method. So what is the gravity? So in my first lecture I have already discussed about the basics, geophysical technique to probe the earth. In there I have told about the gravity. So every object on the surface of the earth is attracted towards the earth center with a force equal to the weight of the object. It is a potential field, that means the force acts as a distance, that means 1 by r square varying. It is a passive method, so from the outside we don't need to give input any energy to acquire data, in unlike in the case of reflection and reflection. So it is the main thing is that unlike the magnetic field, which is very complicated fields, the gravity field is simple field, unipolar, that at a point single positive or negative values of the gravity anomalies will be there. It's completely vertical. It acts on the surface completely normally with the surface. And how and why we study gravity data is to just study about, to know about the subsurface geology. If there is a density of the rocks, there is a higher density of the rocks increase the gravitational attraction, and which creates a positive gravity anomaly, high gravity anomalies. So before talking about all the anomalies, I will discuss in my next slides what does actually mean by anomaly, what is just deviated from the normal ones, that is called the anomaly. So suppose we have observed data and we have a theoretical data. So if you subtract that observed data with the theoretical data, you are supposed to get the anomaly. So, and but negative anomaly will account for the gravity low. Now, it is a very famous Newton's law of gravitational attraction. Hope all of you have read it in class 11, 12 in intermediate courses. So if there are two bodies, that is M1 and M2, they are attracted by the gravitational force of attraction, which is the G M1 M2 by R square. That 1 by R square dependence is the inverse square law. Suppose there is a mass of M2, big mass, and some small mass M1. So the small mass M1 will be attracted toward the big mass M2 with an acceleration due to the gravitational attraction of M2, like Gm2 by R square. This is the acceleration of the mass M1. Now, when we are considering about the Earth's gravity field, that M1, M2 is the mass of the Earth. M1 can be replaced by any mass which is attracted towards the mass, because obviously big mass will attract the small mass. If we have bigger object, smaller object, the bigger object will always attract the smaller object to him, to its to its vicinity. So that r is the that if there is a distance between observation point to the center of the earth, so we can replace the values and m2 mass. The g is the value of gravitational attraction, the mass, the gravitational attraction between the two masses. So we measure the unit of measurement of g in what value, practical value, that is milligal, the gravity measurement unit. Commonly we use that measurement because the when we measure the subsurface gravity variation, it is in very small unit, so we measure it in milligal. 1 gal means 1 centimeter per second square. Now we move to equipotential surface, and what is and why we studying the particular term geoid. It is very important. Later I will discuss its significance. First is the gravitational potential energy, the potential energy of a unit mass and a gravitational attraction. Now my last lecture I have already derived it. How can we calculate? The equipotential surface. Geoid is an equipotential surface. So some assumptions are there in the equipotential surface. We know that no work is done in moving from one point to the another point on the equipotential surface, and the force must act perpendicular to the surface. Our physical equipotential surface is called geoid, which acts actually remains normal to the gravity. So this is our this is our equipotent this is the our normal topography. This is the geoid. And what is ellipsoid? Ellipsoid is a theoretical smooth surface. There is a undulation between geoid and ellipsoid. That difference is called geoid undulation. If the mass is excess, that means there is an excess mass, the geoid actually goes up and it will give the positive anomaly. When there is a deficit of mass, geoid actually goes down below the ellipsoid, that does this point, and it will give negative anomaly. Okay, so you can see that a normal gravity is acting perpendicular to the surface. You are no electric in electric field, and there will be an equipotential surface, and that these are the assumptions for the equipotential surfaces. And why this is the difference, and why there is a difference in the geoid and reference ellipsoid? There is a This actually happens due to the lateral density anomalies. The density is not homogeneous along the arc. There must be heterogeneity in the masses, so that gives rise to the lateral density anomalies, and which is the main cause for the undulation of geoid and our reference ellipsoid. Now, in our gravity field from in intermediate level, people you must have the physics students must have read this centrifugal acceleration. What is the acceleration and how the g is varied due to the centrifugal acceleration? So let me elaborately discuss it. When it is Earth's surface. Suppose we have an observer of mass m, and it is on a rotating frame. So that is called non-inertial frame, and Newton's law is not valid. That is it is a non-accelerated frame. It is an accelerated frame, that means a not is equal to 0. Okay. Now, if it is a mass, so centrifugal acceleration is the acceleration m omega square r. It is m is the mass of the earth, omega is the angular velocity of the frame, not of the object. Angular velocity of the frame on which the object is sitting. Okay, and r is the distance of the object from the axis of rotation. So here in my figure, this is the axis of rotation. You can see the earth is rotating, and there is a mass. On the mass m is mg prime, which you can read. There is a mass mg is acting in this direction, and component wise, if we can divide, that is a centrifugal acceleration m omega square r. This angle is theta, so this angle is also this, and this is the parallel section. So this angle is omega square r cos theta. Along this the component of m omega square r along this angle, and the net force will be acting mg in this direction, m omega square r cos theta. So mg minus m omega square r cos theta. Meanwhile, that small r and capital R is related by small r is equal to capital R into cos theta from this triangle, you can see. Then from in this equation, we can write the true acceleration will be the net force divided by the mass of the object. So that is g minus omega square r. So you can see the component of the centrifugal acceleration, that omega square r into cos square theta. That theta is the latitude at any point. If the object is there, it can extend an angle theta, which is the latitude at the center. So you can write, and omega is the angular velocity of the accelerated frame. Here in our case, it is the earth. You can see that at the pole, theta is equal to 90 degree. So g prime is equal to g. We can have maximum value of g. Centrifugal acceleration plays no role. But on the equator, theta is 0. It extends an angle 0 degree in the equator. So g prime is equal to g, which is the maximum value of centrifugal acceleration. So the minimum value is the g prime. You can see so that centrifugal acceleration plays a big role in the Earth's gravitational acceleration, and in this way we can see that g values varies with the variation of latitude. Centrifugal acceleration plays a big role in variation of the gravity values from equator to the pole. That's why we are having the equator. At the equator, we are having the minimum gravitational acceleration, at the pole we are having maximum gravitational attraction. This is the physical reason for the variation in G. Now, before going to the gravitational reduction and gravity anomaly, we already have derived the geoid things. Now we should tell about the reference ellipsoid. We have a glimpse of some reference ellipsoid in my previous slide. It is the theoretical surface or mathematical surface of the earth, and the theoretical gravity is measured with respect to this ellipsoid with the major axis A and the minor axis B. In our case, the equatorial radius is 6378 while the polar radius is 6357. So the equatorial radius is less and the equatorial radius is more and the polar radius is less. The geoid are now the geoid. It is the equipotential surface of the Earth's gravitational field. So in this figure, you can see the smooth surface, that is ellipsoid. There is a topographic undulation. Hills will be there, mountains will be there, some depressions there will be there, and geoid. And difference in geoid and ellipsoid is called geoid undulations. We have already discussed that. And geoid in average coincide with the mean sea level MSL. All the gravity values are measured with respect to the, or it has to be reduced to a common datum level, that is our geoid. Reference ellipsoid is very much important in case of Earth's normal gravity or the theoretical gravity formula, which has to be subtracted to the observed gravity to obtain the our gravity anomalies. So in that way, ellipsoid and geoid are extremely important. You can see this equatorial radius is more and the polar radius. That's why in the equatorial case gravity acceleration is less, that distance is more, and the pole things gravity acceleration are more. Now when we measure the gravity, there in my previous lecture I have told about the simple pendulum equation, how we measure the time period of simple pendulum. It measures the absolute gravity. In our free fall method we measure the absolute gravity. In practical cases it is very time consuming, absolute gravity, and costly, so the instruments, and we stick to the method of relative gravity. Here is autograph Simtrex gravimeter that measures the relative gravity. The minimum value of gravity you can measure is very less, 0.001 milligal, very accurate and precise value. So let's, I have made something for you friends. You can see that, so that easily step by step we can understand it. Don't worry, it will not be so boring. Let's just see it. First we'll how measure absolute gravity is the weight drop method. First, if a free fall acceleration from t is equal to 0 to the t is equal to small t, we can have that formula of vt plus half gt square. From this formula we can have the absolute gravity values. If we know that from stop was the value of free fall t and the initial velocity with the distance that it covered, we can get the value of absolute gravity formula. And also from the simple pendulum that I have derived, we can get the absolute gravity formula with the input of the length of the pendulum and the time period measured with the stopwatch. Now, in field, in real cases, the relative gravity is more important than the absolute gravity. That is the gravity values between 2 points. Here I will just give you some basic things, glimpse in which you can get an idea in field how the measured relative gravity is measurement. This there is a, suppose in one station in we measure there is a spring and the mass system, and the force exerted on the block is F1, that is a F2. If there is a gravity, there is a length of the spring. If the gravity is more, then that length between two stations of the spring, that is more, because the L proportional to G. That follows the gravity formula. F is equal to mg in at any point, the force that mass exerts on a string, where F1 F2 you can see the weight of the mass at stations 1 and 2. So you can find the value of g from the force exerted divided by the mass. When there is a more gravity, the length is more, length of the string, and the spring contracts when the gravity is less. In real case, what we do, suppose we measure the gravity at particular point, it's called base station, actually, where we know the absolute gravity values. It is known, Then we move from that point to station 1, station 2, 3, 4, likewise, and we end our measurement at again at the base station. We complete a cycle type things. Here is the paths of the survey, and we calibrate the gravimeter so that the delta of the gravimeter that we measure, it is represents in milligal value, that means in a gravity unit. And so gravity can be computed by adding the value of delta G. We know the absolute gravity of the base station, and we measure the gravity by computing by adding or subtracting the value of delta G. It compensates for the gravity loss or more gravity. And at each station, what we measure, the length of the spring actually recorded, as the length of the spring is proportional to the gravitational acceleration. So in that way, you can measure the absolute gravity with a gravimeter, Centrex gravimeter. So this is just a glimpse of the method in field. You can see it. So our geophysicist friend can have an idea of how to measure gravity, actual relative gravity in a field. It will help them a lot. Now, actually, in after taking the readings of the gravity, we have to reduce the gravity value to a common datum plane and the gravity anomalies. So what do you mean by gravity anomaly? As I already discussed, the observed gravity, what we measured, and the normal gravity value, that means with respect to the ellipsoid, that gives us the gravity anomaly, anything that is deviated from the normals. But that gravity anomalies or readings are influenced by so much of factors. There will be drift, latitude correction. Already I have given you some glimpse of that. Elevation, topographical things, earth tides. That correction we must apply to reduce the gravity data to geoid. Geoid is a common data plane. So these are the corrections one by one. Just let me give you some idea of that. There is a latitude or normal correction. You can already see from centrifugal acceleration slide that how the gravity values are variations are there with the latitude. The centrifugal force reduces the gravitational attraction, and due to the shape of the earth is not a perfect sphere, it is an oblate ellipsoid. You can see it is a bulging at the equator and rotating about an axis through the poles. The normal gravitational formula that is measured with respect to the ellipsoid is varied with the equation. That means there is a value at the ellipsoid, that is the equatorial value, and with the formula of sine square phi sine to the power 4 phi a and b. If you can see for equator, that angle is 0, and at the equator gravity value is less, and the poles angle is 90 degree, that value is 983. It implies the non-spherical shape of the earth because bulging at the equator and shrinking at the poles, and this distance equatorial radius is more, I have told ample times, 6378, and this distance pole radius 6357 is less, and due to this accounts for the factor of less and more gravitational attraction, and it is also associated with this formula. First, we move to the drift correction. What is the drift? If we keep the gravimeter at a particular place, the value at a single station changes with time. Why this happens at a single station? The question may arise. There are so much of factors. Environment change is there, mechanical jolt is there, spring creeping is there, and there is also a tidal effect, that is rotation of the earth, moon, and the sun. So how can we compensate for the factor? We take the initial reading and the later reading, that is distributed linearly between linearly to the intermediate stations, and then we have to calculate the drift rate. That means the difference between the readings divided by the time difference. Then the drift correction factor is the drift rate multiplied by that delta t. But delta t is the time difference between each station and the base. To compensate for this effect, we have to reoccupy the base ample times. The drift behavior is the specific to a single instrument and must be measured for this particular instrument must have particular drift. All instrument has not carries the same. Now let me show you the very important these things for gravity. In case of gravity anomaly, free air correction or free air anomaly is very easy. Just don't be bored. Yes, I will be giving lecture. I will be elaborately describing you to a very simple manner. This list you can see there is a shape of the Earth. Okay, it's the equator, and that is the radius of the Earth, and it's extend an angle with the equator, that is the latitude phi. There is a station and it actually accounts for the elevation of the station from the center of the earth, this extra distance. Now the gravitational acceleration related to the formula, if we make a derivative we can get dgdr is equal to minus 2g by r. Dgdr means the average value for the change in gravity for the increased elevation. And if we replace the value of that the radius of the earth and the small g, that average value, assuming the average value of g, that is calculated to be estimated to be minus 0.308 millical per meter. That means for every 1 meter distance, for every 1 meter elevation above the surface of the earth, that gravity values decreases with the decrement of the gravity value is 0.308 milligal. Here is a sea surface, that is the topography, and the station is above the level. There is a pictorial depiction. So free air correction is that height into 0.30. To compensate for this gravity loss, we have to add this value of gravity to our observed gravity value along with the theoretical correction. So I hope it is clear to everyone. But in here, h is the elevation of the station above the sea level datum. H or this delta, that is elevation of the station above the sea level datum. So how? So what is the then free air gravity anomaly? That the observed value subtracted from the theoretical gravity, that is the gravity anomaly, it has to be added with the free air correction to compensate for the gravity loss due to the elevation of the station from the center of the earth. Okay, now second, station is above the, now the next very important thing is the Bouguer gravity anomaly. So what is that anomaly? So let me discuss it. Suppose there are two cases, there is in the land and there is in the sea. In the land, suppose there is a station is above the sea level datum, so there will be in free air correction, there we have not assumed any mass between the station and the sea level datum. So there is a mass is there, the mountainous or hilly area have extra gravitational attraction. So in what way we can defend that? So these extra masses account for the Bouguer gravity anomaly. So in applying this formula, we assume a infinite slab of thickness h equal to the distance between the station and the sea level datum. That infinite slab, and the density of the slab is the average density of the granite rock, 2.61 gram per semi-cube. So there is this is the station, this is our topographical effect, this is the infinite slab. So we can, our Bouguer gravity correction is actually 0.04 rho into h, that is at the Bouguer on the land Bouguer gravity correction. If we substitute the value of rho, the Bouguer gravity correction is h into 0.112, and at the sea that rho value has to be replaced with the value of the water and the density of the concrete. In at the sea the case is opposite, it is sea level and actually there is no concrete, so we have to assume the that plane infinite slab with the thickness equal to the height of the water bottom, that depth hw, and rho w is the density of the salt water and rho c is the value of the concrete. But actually let's see the free air correction is 0 because there is no height h. If we assume that hw, then Bouguer correction becomes that hw is 0.0687 millical per meter. So a free air correction has to be added to compensate for the gravity loss, but the Bouguer correction on land has to be subtracted from the free air value to compensate for the more gravity. Okay, so in the sea you can see the pictorial depiction. This is the topography on the land, that is the station is above the base, it's the density of the rock, and for Bouguer this is a station, and the sea, that is the this height is the sea water, the depth of the sea water we assume that fills with the concrete, no concrete is there, then that rho is 1.6764 gram per semi cube. Okay, this is sea level here. So the pictorial depiction of the Bouguer gravity anomaly at the sea and the what at the sea and on the land. That correction is very much needed to for the gravity anomaly. Now, in addition to the Bouguer gravity anomaly, we can see that the station, in the vicinity of the station, there will be topographic undulation. So there may be hills and there may be valleys. For the two cases, the gravity anomaly reduces because for the for this, if we consider the case of one, there is a mass of the mountains over the slab. You can assume, and that because of the upward force that reduces the gravity values, and actually this too is the lack of downward force. So in both cases the gravity value reduces, so the terrain correction, which accounts for the surface irregularities, is added in both the cases. In mineral exploration, that is very useful in hilly terrain. Okay, that is added in mineral exploration. This is often used, the terrain correction terms. Now, forget about land. This is for the moving vehicle correction, that is Eotvos correction. This is carried out usually on the ship or the aircraft which is moving. What is the correction? Correction, you can see it is dependent on the value of the latitude and some sign of the angle. It is the direction with respect to the north, angle with respect to north, and the velocity of the ship in the milligal. And now it has to be same thing. It is positive when the ship is moving to the east. What happens when the ship is moving to the east? It is moving towards the earth centrifugal acceleration, so that the gravity value decreases. So you have to add that value. So that's why delta G is positive. Now it is moving to the west, it acts opposite to the centrifugal acceleration, the gravity value decreases, so it has to be subtracted, so it is negative when it is moving westward. In simply in that way you can think of that. So when you are doing marine gravity survey, that Eotvos correction has to be taken into account, or the air, or in the aircraft survey, airborne survey. So now let's recapitulate the gravity anomalies. What are the first three air anomaly, one by one? So we are having observed gravity value. We have to subtract a theoretical gravity value that gives the gravitational gravity anomaly, and the free air correction has to be added to compensate for the gravity loss for the extra elevation. Next, we are having Bouguer gravity anomaly. Opposite to that, free air anomaly. From the free air anomaly, we subtract the value of the infinite slab, that 0.0419 into rho into h. So the extra gravity value for the extra mass of attraction has to be subtracted from the free air gravity value, that gives rise to the Bouguer correction. And if we substitute the average density of the crustal rocks, then the value then the formula is delta GFA into the this factor into the height. That means the thickness between the station and the sea level datum for the for assumption of the infinite slab. Now on the C, what happens? On the C, that H is replaced by HW, rho is equal to rho W minus rho C. I've already described, and the value reduces to that delta GFA plus, this is the value of gravitation, the Bouguer correction at the C, that has to be added because the C is below that's below the sea level datum. We are doing the calculation, so that plus signs come. GPS is the anomaly at C and H is the water depth below the observation point. Complete Bouguer anomaly means we have to take into account the terrain effect. When we add the terrain correction with the Bouguer anomaly, it gives rise to the complete Bouguer anomaly in the milligals with the terrain correction. So this is our complete formula of how we derive the gravity anomaly, how, and after reducing to a common datum plane, that is geoid, and how can we describe. So what is the logic behind addition and subtraction? Always uh, always that remember one things, for if the station is above the base, the free air correction has to be added. If it is below, it has to be subtracted. Similarly for land, if the station is above the sea level datum, that in the land, that Bouguer correction has to be subtracted. And for the for the Bouguer anomaly on the sea, that amount, that value has to be added with the free air correction. In that way, the free air anomaly actually mimics the topographical effect. The Bouguer anomaly is comparatively more smoother. Okay. So this is our complete recapitulation of the gravity anomaly. Hope you have enjoyed, and you are having some, if you are having some doubt, you can mail me on my mail account, or you can directly comment on the YouTube link section. I'll be happy to address your queries. Don't forget, if you really benefit from my channel, don't forget to like and subscribe to get notified or for more updates. And on requirement, I will be giving some numerical problems on the gravity, so that it can just strengthen your basic things on the gravity values. Thank you.